I need somebody to check to see if they can hear me.
Yeah. Hey, anybody online, can you guys let us know if you can hear us? Oh, sweet, Hoda. Okay, Hoda, thank you.
She
Okay,
said
you're
yes.
good. Yep, you're
We
good.
can see. Okay, good.
Yay. Thanks, guys.
All right. Come on, wake up.
Try doing it, yes. But just in case it was that, you just, it was really weird because like everything up there was just like, oh, I saw it all.
A little squished, but it'll do. Okay, so this is a continuation of the lecture from last week. And as I mentioned, we're going to, Matthew made the comment that we did 2 semesters of computer science in 1.5 hours. This week we're going to do the other 2 semesters of computer science in an hour and a half. So again, things will move quite fast. Mostly, as I mentioned before, this is to give you a familiarity with the topics, not make you experts in the topics. It's to give you enough knowledge to know that if it's something you don't understand, you need to go ask somebody, right? But it's so you can talk to people intelligently about it. All right, so we're first going to talk about networks and network topologies. So, last week we talked about a computer system and the von Neumann architecture, where you have GOSINTAs, you got inputs, outputs, a processing unit, memory as temporary storage, and that's a single incident. And so some of the inputs and outputs could be coming over a network. And in fact, in modern days, machines that are not connected to the network, as you could see by us not being able to connect to Blackboard a little while ago, can really mess life up. All of us are familiar with the code purples. The last several code purples had to do with lack of network on campus. And so understanding networks is important, not necessarily for you as an individual, but being able to talk intelligently to the network engineer who's going to fix it for you is important. So networks come in a wide variety of flavors. A lot of them are differentiated by the topology that they're using. So you can have, so a topology is the pattern of links, how the different nodes or computers on the network are interconnected with each other. And your choice of topology determines how resilient your network is, how reliable it is it going to crash, is it not going to crash, it has to do with redundancy and scalability, how much data can get through that network. The simplest network is just 2 nodes talking to each other point to point. More complex networks are built up by adding more and more of these point-to-point connections. And the question is, what do those point-to-point connections look like? So for example, you could create a ring where each node is connected to a partner on either side of it. This is quite a simple topology. It can be somewhat reliable, but it has the problem that if I'm at, for example, the topmost node and I want to get to one of the bottommost nodes, I have to pass through all the nodes in between to get there. So there's a lot of hops, and that could, as you get more and more traffic on the ring, it gets more and more congested and becomes less and less reliable. A similar topology is a line where they're not connected. The last node isn't connected to the first node, but it has the same problems as a ring. So to get more resiliency, typically you start doing either some sort of centralized mechanism, such as a star, where there's a central node talking to a whole bunch of satellite nodes, or a tree, where you have one node that is branching out to talk to various leaf nodes. That tends to increase the bandwidth of the network, but then everything concentrates at the central point, either the center point in the star or the root of the tree. And so that node, if it isn't well designed, also could end up being the congestion and choke point that doesn't allow the topology to go. So often you'll see you start making additional connections, either a mesh that is partially connected, such as this one where you have essentially a couple of rings and a line, if you will, or a fully connected mesh where every node sees every other node in the network directly in a point-to-point connection. Obviously, that's the one that has the greatest throughput, the greatest resiliency. It's also the most expensive to build, and becomes impractical as you start scaling to thousands and thousands of nodes. You can't have a single computer that has 1,000 connections out to all the other possible computers that it wants to talk to. The most common network of a few years ago was something called a bus. Okay, and that is where it's like speaking in a crowded room. As long as there aren't too many people in the room, they can hear each other's conversations, but as the room gets more and more crowded, the bus gets more and more congested, and eventually it will fail. Pardon?
What would Tor? Tor, T-O-R.
A Tor?
Tor is a peer-to-peer military network.
It's a military network?
Yeah, for decryption, onion network, all that stuff.
Yeah. I don't know what topology that is, so I can't, because I'm not familiar with that network. So, yeah, that would have been my guess, is that it was some form of a mesh network, because most of the military networks are some form of a mesh network. A mesh network, in terms of the previous slide we were looking at, they are not necessarily fully connected, but they have enough redundant connections that you're not worried about losing connectivity if you lose a connection. Most modern networks these days are meshes. So, for example, here at UAMS, what they're trying to do is create essentially a pair of mesh networks so that if one fails, the other one takes over. That's how they're trying to eliminate the code purple. So we'll see if they are manage to do it. So networks, the nodes talk to each other through what are known as network protocols. And a network protocol typically starts with a handshake where you initiate a connection. The other side will acknowledge that I got a message. There are payloads. That's the data that's being transferred. And there typically are multiple protocols for different purposes. So depending on what you're trying to do, you may be using a different protocols. And we need to make a distinction here between what's called a network protocol versus a data or encoding standard. So the protocol is how the payload, the message, gets moved from place to place, whereas the data or encoding standard defines what's in the message. Most protocols, not all, but most protocols are agnostic to the content of the payload. All they care about is the routing of that payload. The most common protocol, which you all are using, whether you know it or not, is the TCP/IP stack. TCP is the transmission control protocol. IP is called the Internet Protocol. As the name suggests, that's essentially anything you do when you're doing web browsing or email. It's all using TCP as an underlying protocol. Years ago, back in the 70s, they created this 7-layer model, and this 7-layer model still applies today. People still use it for interconnecting systems. And the reason they created the layers is just to make it easier for people to build the components that are needed to put together a network. And each layer builds on top of the previous layer. So if you start at the bottom, the lowest layer is what's called the physical layer. So that's essentially the wire or the radio waves that are used to move bits of data from point to point. that it's the signaling, is plus 1.5 volts. Is that a 1 or a 0 if we're talking about a digital binary protocol? So that's what they mean by the physical layers. How do I actually send the information? One of the the next layer up is what they call the data link layer, and these typically are the point-to-point connections between nodes. And it's the low-level signaling is how do I get a frame of information, a small chunk of information, typically about 1,000 characters, from one spot to another spot on the network. But usually you don't want to talk just to the node that's next to you. You want to talk to somebody somewhere else, and that's where the network layer comes in. It deals with the routing of these frames or packets between nodes in the network over the topology. So the network layer is the thing that's aware of the topology and is aware of how do I route a packet to get it from point A to point B. Now that gets you just a single packet, but typically when you have a conversation, your conversation is longer than a single packet. So that's where the transport protocol comes into play. So it's the thing that that essentially makes sure that your data gets from your node to the proper destination. Session, presentation, and application, typically at that point your message has gotten there and they deal with the interpretation of the message and what you do with it. So session typically has to do with authorization and authentication. A presentation has to do with how is the message encoded, and the application is, well, what do you do with it? To give you a better example, here are some of the protocols that you may have heard of in the various layers. So at the application layer, HTTP, when you type HTTP to go to a web browser, you're actually using a protocol that goes from your computer to some web server someplace saying, I want a piece of information. And that protocol is called Hypertext Transfer Protocol. File Transfer Protocol is another typical where you're moving a file from one system to another. Simple Mail Transport Protocol. These are all things. Those are protocols that operate at the application level. Presentation level. If you ever added an S to your HTTP, what HTTPS is not a different protocol than HTTP. What it is, it's HTTP running over the TLS protocol, which allows for secures the communication pipe between you and the web server that you're trying to talk to. That's an example of a presentation layer protocol. Session layer would be how do you find things. So LDAP for directory access to be able to log into systems. Remote procedure calls, that's at the session level. Transport, we already talked about TCP. Network is that IP. So those two protocols we talked about, one of them is at the transport layer, it does the end-to-end communication. The other one is at the network layer, it deals with routing of the packet. And data link and physical, the most classic example, of course, is Ethernet, either the plug-in kind that you plug into the wall or the wireless that we're using to communicate typically with our laptops and handheld devices. The physical link, that's where you get into things like DOCSIS. That's the protocol that uses cable television technology to be able to move data about. DSL uses telephone technology to move data about, and the lower layers of Ethernet. So to give you an analogy of how all these layers work, let's say John wants to dictate a letter to Mary. So he dictates the letter, and what Mary gets is the content of the letter, and neither one of them are aware of everything that went on to get the letter from John to Mary. Okay. Well, let's say, for example, that John speaks Russian. He doesn't speak English. So in the presentation layer, one of his assistants, let's say Jan, actually has to transcribe his message into English so that Mary will be able to understand it. That's what is meant by a presentation layer. It's making that message understandable to both sides. Jan will then place that letter in an envelope, possibly with other sheets of information that tell Mary who John is, so that she would trust him, for example. At that point, John gives the letter to a courier. Now, a courier is likely going to stuff the letter into a bag with other letters, right? And he's probably going to add additional information. If you ever sent a letter through the post office, I know that's kind of old hat these days, but if you ever notice when you receive a letter, there's often a little code on the bottom of the letter that's printed on. That was added by the post office. That would be akin to the transport layer, where it's trying to add the information needed to get that letter from you to somebody else. The network layer would be, if you've ever sent something with, like, for example, FedEx or even the post office, if you bought tracking information, the network is, from here it has to go to the Little Rock Distribution Center, from there to Memphis, from there to wherever John or Mary are. So that's the network layers. How do I get it from place to place in order to get it to its final destination? Between the facilities, it might be, for example, thrown into a big container with other letters and shoved onto an airplane that actually, or a truck that moves it through the air or on the highway. So that's the analogy of what we mean by the layer. So each layer has a specific job. And it makes it easier for the designers, when they're designing networks, to think about it in these layers. So when you hear somebody talk about, well, that's a layer 3 protocol or a layer 7 protocol or a layer 4 protocol, they're typically referring to these OSI layers. Telecommunications. These standards are becoming more and more important. Typically, the wired standards were pretty much, the world is pretty much settled on Ethernet at this point. The 802.3 protocols as defined by IEEE. Telecommunications, those protocols are still all over the map, depending on what you're trying to do. So for short range, for example, my cell phone can communicate with your cell phone just by tapping them, right? You've probably played that game. That's using a protocol that's called NFC, which is a near field communication. It's a particular data and physical link protocol that allows the two devices to communicate with each other. RFID is a similar sort of protocol, but instead of being 2 ways, it's 1 way. If you've ever been for example, I go to the RSNA conference every year. They know exactly where I've been because on my ID badge, there's a little RFID tag. And as I walk between, there are these receivers that determine where I've been. And so my credit, my CME credit, is totally based on that little badge. If I'm sitting in a room, they know I'm listening to that lecture, and so they give me credit for that lecture. So those are short-range protocols. They typically only work within at 10 meters or so, sometimes less. Medium range would be the wireless that we're talking about. Again, almost ubiquitously wireless Ethernet, although there were at one point other potential protocols there. And long range, those continue to evolve. WiMAX, CDMA, 3G, 4G, LTE, you've probably heard all these terms from your cell phone providers. Those are all what we call long-range protocols because they typically go for kilometers as opposed to just meters. And it goes without saying that wireless has really changed the face of the world in medicine. From the telephony to, doctors used to always carry pagers, right? Some of you might be old enough to remember pagers. Have you seen a doctor with a pager lately? Almost never, because they're using their cell phones either through SMS text messaging or just simple phone calls. So things change over time. And a lot of the devices that you see out there are now wireless and networked. I think I may have skipped ahead one. If you want to know more, of course, there's lots of places to look. The problem with the networks, of course, is that how do you maintain the security of the data? And there are a number of rules and regulations that have to do with the data, the security of the data. These are just the ones from the US. So I work for the International DICOM Committee. That's just the beginning, right? There's a whole bunch of rules that from other countries. Fortunately, they all tend to be very similar, but there are lots and lots of regulations that deal with protecting data. So, quick trivia question, try to wake you up a little bit. Can anyone tell me what HIPAA stands for? Now, if you're paying attention, it was on the last 2 slides, but let's see. Health Insurance Portability and Accountability Act. Okay, and what was the main focus of that legislation? Why did Congress pass it? To do what?
Privacy.
To privacy of the healthcare information. Okay, if this were HIPAA, the privacy is that much of it. With whom? So to share health information, but with whom? With other insurance companies. So the whole idea behind HIPAA was that portability part. That's where they started when they created the legislation. The whole idea was to make it so that you or I could move from company to company and take our insurance with us, or at least our coverage with us. So that was the purpose of the legislation, was so that you don't lose coverage if, for example, I change employers and I go to a different insurance company. But the insurance company said, well, in order to do that, we have to share our records. So the bulk of HIPAA actually has to do, the mandate in HIPAA to the government was create a set of standards for sharing these records. Okay? And then the privacy advocates came and said, well, wait a minute, if you're going to share those records, how are you going to keep people's privacy protected? So the privacy rules actually were an afterthought that was added to the HIPAA legislation during the legislative process, of course, not after it was passed. But to protect the privacy of individuals when moving these electronic health records around. So, and over the years it has been expanded. So HIPAA is these transaction and code set standards. That's the main focus of HIPAA. But over the years, the other things, the privacy rule and the security rule, have taken on the major importance, so that as most people, when they hear the word HIPAA, they're thinking of the privacy and security rules, not the portability part of it. So the HIPAA security rule from the old legislation says that covered entities have to ensure the confidential integrity, availability of information. It has to protect it, has to, against anticipated threats. It also has to protect it against inappropriate uses or disclosures. And the rules say you have to ensure compliance of your workforce. So that's what the initial rule said. Confidentiality, their mean is to make sure that somebody who wasn't supposed to see a patient's record doesn't see it. Integrity means that a record cannot be altered or destroyed. And availability means that if the record is there, those folks who do need to see it have to be able to get at it. So it's more than just privacy. The security rule really is saying that if we're going to make things electronic, you have to make sure that they're protected, that they're available, and that they can't be changed. That's the whole purpose of the privacy of the security rules within HIPAA. HITECH was a follow-on legislation from a few years back, which really beefed up and clarified some of the issues within HIPAA, in particular some of the enforcement issues. And we're not going to go into a great deal of detail about HIPAA and governmental regulations. I think you get that next semester. Is that what you said, Meredith?
Yeah.
So this is kind of just to wet your whistle. But what we do want to go through is some of the technological means and steps that one has to go through, just to give you a flavor for that, so that if you were ever involved in these as an informatician, you kind of have an idea of what's going on. Again, I'm not expecting you guys to be experts in these fields, just familiar enough with them so that if you're called upon to play a role in a committee that's evaluating, for example, privacy policies, you have an idea of what some of the people are talking about. So one of the things that the high-tech regulation started to enforcing is that entities had to do what's called a security risk assessment. So what is it? And there are other federal regulations like FDA and some of the others that also require these security risk assessments. And oh, by the way, they're probably a good thing to do even in your own personal life, believe it or not, to do a security risk assessment, to say, okay, where am I vulnerable? What could impact me? So how do you do a security risk assessment? You have to create an asset list. What are the things I want to protect? You do an evaluation of the threats and an assessment of the risk associated with those threats. In other words, what could happen? How likely is it that it's going to happen? And how bad would the damages be if it happened? Okay? If I have a $20 savings account that I had from when I was a wee kid, the damages, if it got compromised, are probably minimal, as opposed to my wife's brokerage account, because she has all the money, where the damages could be significant if that one were compromised. You then, so using that information, then you set either policy, education, physical measures, or technical measures to try to deal with the threats. And typically what you're doing is you're building layers or rings of protection. So typically you don't have everything, just one thing that's protecting your data, but rather you're constantly evaluating of what are the various things I need to do to protect that data. And how much of that is commensurate with the risk, which is why you have to sit down and do the risk assessment, is to figure out how much do I need, what do I need to spend, what do I need to do in order to counteract the threat. So you have to start by acknowledging that no system is perfectly secure. No matter how hard you try to secure a system, someone is going to find a way into it. It's just a fact of life. There's always going to be vulnerabilities. So the idea, yes?
Just a quick question. On something like TCIA, the Cancer Immunity Archive that you run about, how often do you guys get security threats if you're sort of managing that live system? Like how prevalent?
How prevalent?
Yeah.
It's something that we're constantly monitoring, so we don't ignore it. And we have the TCIA system. Now keep in mind, TCIA does not have any, shall we say, monetarily valuable information in it, if you will, because everything's publicly available and anybody can download it. However, we have been hacked at least, TCIA has been in operation for 7 years, and we've been hacked at least 3 times over those 7 years. So every time we're hacked, we take steps to go back and evaluate why we were hacked, or how we got hacked, and then to take steps to make sure it doesn't happen again. Fortunately, because of the layers of protection that we had when somebody did hack in, the worst they were able to do in one case was to set up a pornography distribution site. So, well, I mean, it's an image repository, you know, why not?
It was
So, so it's a matter of identifying those and then dealing with them, right? So you have to identify risks specific to that access based on the threats you perceive that it's going to receive. And then you implement security controls to reduce the residual risk to a point where you say, okay, that's good enough, right? It's never going to be perfect. You just have to get it good enough. And then monitor for incidents. You know, and when you monitor for incidents, that might lead to corrective action. It could also lead to the word that we don't want to hear, which is sanctions. The problem is the more secure, I mean, I've dealt with some of the systems over at the VA, for example, and some of those systems are so tightly locked down that you can't really do much with them. So you have to balance the ease of access and ease of use against the threat. You know, in certain cases they have to be locked down that tightly because the risk of damage is so high. In other cases they probably don't. So I think we've somewhat covered this area. So for each risk you have to evaluate its impact. You know, if that particular threat happened, what would be the potential for damage, and how many components how widespread would it be? How many components would be affected? That would be the impact of a particular risk. The possibility is, okay, but how likely is it to occur? So you might have a risk that could be really devastating, but the likelihood of it occurring is extremely small. And then the other one is the ease of exploitation. You know, how easy is it to find that risk and exploit it? So those are some of the key factors you would look into. How do you do the risk assessment? Most often it's done by self-assessment by the owners of the asset. So whoever owns the asset does the assessment as to what's the impact and you know, how exploitable it is. Sometimes there will be an internal group that does that assessment. Sometimes you'll call in somebody from the outside to do the assessment. You know, which of these methods you use depends on probably an initial triage of how significant you think the risk might be, and how valuable the asset you're trying to protect is. Measurements can be qualitative and quantitative. You know, a numeric score versus just a basic binning of high, medium, or low. Most people use the qualitative variant. And then the management is, can I live with the risk? Or do I mitigate the risk, take steps to make it so that it doesn't happen? Or can I do what's called risk transference, which is somehow deflect it so that it's somebody else's problem, not mine, preferably somebody else who can handle it better than I can handle it. And so you determine the assets, and you know assets have an associated characteristic. They have a value. Each asset has controls. Those controls cost money, and the idea behind the controls is to reduce the risk. But controls have vulnerabilities that could be exploited to get around the control, which can create incidents. And those incidents, then you have to deal with resolutions. You can either improve the controls, but it may lead to sanctions. And those risks, whoops, sorry about that. Come back. And in all of this, you're always constantly trying to measure the risk to determine whether it's not acceptable and you need to improve the controls, or whether it's acceptable and you just go on and live with it. And those controls can either be administrative, physical, or technical. So administrative control, an example of an administrative control would be an acceptable use policy. How many of you have tried to stream a local sporting event here on campus? You're laughing. Does it work? No, no. One of the code purples we had here when Epic went down, I found it quite amusing, although the network engineers told me it had nothing to do with it, but I found it quite amusing. The code purple started right about noon and ended at 3:30. And the Razorbacks were in the NCAA tournament. Their game started right about noon and ended right about 3:30. Coincidence? I don't know. But it just goes to show, despite the fact that streaming of sporting events was illegal, I have a feeling that some folks found a way to get around that control. Okay? But administrative typically has to do with policies, things that you write down. How often are you supposed to change the password? What are you supposed to do with Social Security? Do we ask for them? Do we not ask for them? Business associate agreements and contracts and training, and those are administrative controls. So physical controls would be trying to protect the asset, the physical access to the asset. So for example, to get into the main computer room for the campus, first off, you have to know where the building is. That's sort of a weak physical control, but once you figure out where the building is, your badge has to get through a card reader that recognizes the badge, plus you need to know a PIN to get into the building. And then once you're in the building, you still can't get to the computer room. You have to go through yet another badge reader to actually get into the computer room. So multiple layers of protection, but that's physical protection. Technical protection would be things like firewalls or writing code in a particular way to protect the data. That's what they mean by a technical protection. So when you're creating these controls, those controls can either be administrative, physical, or technical, depending on the nature of the threat and how you're trying, and the risk of the threat and how you're trying to mitigate it. So as we mentioned, that these security layers, typically the layers, you typically have an element of all of these things. So an element of physical as one of the rings. This is security layers that protect your asset. The networks, social, which would be policies, software or data. You protect. So in case the threat does happen, you minimize the amount of loss. And I think if you were to walk around and just have these sorts of things in mind, you might see examples where these controls could be improved. For example, let's say you're walking on the floor of the hospital. Almost every nursing station has terminals, right? If I'm walking by the nursing station, can I see the terminal? Well, that possibly is something where we could put a physical control somehow to prevent me from seeing the front of the terminal, if the answer is yes. Could I walk around the counter and start typing on the terminal? Will somebody stop me? Will the terminal itself prevent me from typing on it because I don't have a properly coded ID badge? I mean, those are the sorts of things that you consider when you're doing setting up the controls and setting up these security layers. So authentication and authorization, people often confuse these two terms. So authentication has to do with who you are, to physically identify the individual. And how many of you heard the term multi-factor authentication? You're a computer scientist though, right? No, not really. Do you want to give us an idea what do we mean by multi-factor authentication?
Well, you have more than one way of verifying your identity. It's pretty advanced.
I see.
Corporate accounts. So
Yeah.
you're required to have a login and password, but they also had a specific ID generator that they were required to as well. So it's having typically, you know, like a text message to your phone to verify, another way for that to your password, so that you don't just have a single point of access, that you need to have two separate items together.
Right. So that's the idea. If you're doing multi-factor, it's not just a username and password. That's one factor. You need something else besides username and password in order to gain access to the system. Yes.
It's based on a pair or multi-housing pair. It's something you have and something you know.
Right. It actually can go beyond just that. So the pair, typically you want to take at least two things or possibly more, depending on how much protection you need, of one of these four things. Either a physical token. So the example of it sends you a text message on your phone. What's the physical token? Your phone is the physical token. If you don't have your phone, you're not going to get in, right? What's another physical token? An ID badge could be a physical token. So that's one of the factors. Another class of factor is secret knowledge. So to get into the primary data center building, I have to have a piece of knowledge that theoretically only I know, my PIN. You know, same thing with you getting into your account on an ATM. You have to have something physical, your ATM card, plus something, some secret knowledge, your PIN. And you can add other things. So biometrics is another one. My phone opens up, and probably several of yours opens up with a fingerprint. My computer opens up with a retinal scan. So those are biometrics. And the last one is location. So if I were to walk up, if they've done it right, and I'm not saying they did or didn't, if I were to walk up to one of those nursing station terminals, and if the screen were locked, and if I tried to unlock it with my username and password, what should it do? It should say, naughty, naughty, you're not authorized to access this terminal at this location. So physical location is also another way, another factor that one could theoretically use as the multiple factors in multi-factor authentication. But authentication all has to do with identifying who you are. Authorization, on the other hand, is, okay, now I know who you are, what are you allowed to do? You know, so even if I could log into a terminal at a nursing station, if I tried to open Epic, it won't let me because I'm not authorized to see Epic. Okay. Now, the downside is with security, stuff is going to happen. Incidents are going to happen. So what do you do with them? You have to determine, you have to then characterize the incidents. Were they malicious? Was somebody actually trying to get in and destroy data, or are they just opportunistic? So in the case of TCIA, it was opportunistic, where when they put up the pornography site, they said, "Oh, look, free servers." You know, that's an opportunistic. Sometimes it's accidental. You know, you spill coffee on a keyboard, and it all of a sudden the nursing station doesn't have access to the network. My favorite was we had a digital connection between one of our angio suites and our computer, and all of a sudden it stopped working. And we go hunting around, and there were workmen who were trying to clean out the cable cutter. They found a cable, they didn't know what it was, so they cut it. It was our access cable. They didn't mean to. It was an accident. So you try to characterize the type of incident and then deal with it. So you detect it, you investigate it, you report it, try to correct it, and keep it ready for audits, looking for ways to improve things before another incident occurs. We'll skip over breach notification. For those of you who are HIPAA aware, you may be aware that if you are the perpetrator of a HIPAA breach, there's some serious penalties. I don't look good in an orange suit. I never want to be the cause of a HIPAA breach. Okay. So some of the technological means we talked about were firewalls, and I think, does anyone here not know what a firewall is? So, basically it's either an appliance or a piece of software that restricts access to a subnet in a network. Virtual private network is a way of taking a communication channel from point A to point B, passing it over the public internet, but keeping it protected as if it were its own direct wire, even though it's using public wires. And typically, things like virtual private networks use encryption. We're going to talk just a wee bit about encryption. There are two main kinds of encryption, what's called public key or asymmetric encryption, and private key or symmetric encryption. And the difference between the two, as the name implies, public key is actually a key pair. I have a private key and a public key. I publish my public key to all those people who need to see it. So for example, a website, your bank, publishes its public key so that everybody knows what the public key for the bank is. But then when you set up the secure communications channel, internally the bank uses its private key, which they keep under lock and key and well protected, so that, and I can determine whether or not they're using their private. I cannot decrypt a message from them. So if they encrypt a message with their private key, you have to use the public key to decrypt it, and vice versa. If I encrypt something with the public key, the only person who can decrypt it is the person who has the private key, assuming that somebody hasn't broken the code. So that's what public key encryption is. It tends to be a lot slower because the keys have to be a lot bigger. Typical public keys nowadays, public key pairs, run 2048 bits, sometimes even larger. Private key or symmetric encryption is based on a shared secret. So we both know something, like a passphrase. We both know something and we can keep our connect channel encrypted because we both know that something and nobody else knows it. The advantage of symmetric encryption is speed. So in symmetric encryption, you typically can encrypt and decrypt a lot faster than public key encryption because the keys are a lot smaller. Instead of being thousands of bits, they're only hundreds of bits long. Okay? There are other encryption technologies out there like Kerberos. Other things that are used within encryption are Kerberos, which is a way for exchanging keys, lightweight directory access, another variant of exchanging keys, a secure shell for secure remote. Those are some of the things that use encryption. So if you were to look at the handshake in TLS, the transport link security, the S part of HTTPS, what's going on there is when you first start, you're using public key encryption. Remember, it's slow. And they use public key encryption to do what? To exchange the shared secret that you will then use for private key encryption for the rest of the conversation. So they use public key encryption to get what they call a session key, and then the session key is used for the rest of the time that you're communicating with the website until you break off the connection. In some cases, it will rotate through those private keys. So for public key encryption, some popular algorithms, the most popular is RSA. It's getting a little bit old. It's still considered secure, but a lot of people are moving to what are called the elliptical curve algorithms. So if you were to ask which one would I prefer, elliptic curve. They're faster and more secure. Symmetric, there's data encryption scan, there's the old standby. I would not recommend that anybody use it. If you were to send me a message that was encrypted using DES, my phone could probably decrypt it in about 3 seconds. It's not secure anymore. It protects things against prying eyes, but it's not considered secure. Triple DES is popular with older systems. Basically, DES run 3 times. Also, now no longer considered secure. Advanced encryption standard, and then again, there's a number of these elliptic curve algorithms in symmetric encryption. Secure hashes are kind of like a one-way encryption. We'll talk about a little bit more about them. And in Wi-Fi, you've probably heard of WEP, WPA, WPA2. Those are protocols that use encryption. So a hash function is something that takes something that's of arbitrary length and scrunches it down into a single number. It's a form of binning. Okay, some people call this a checksum or a hash value or a hash code or a hash sum. A cryptographic hash, though, has special properties over normal hashes. So in a cryptographic hash, the idea is even a single bit change in the message will make a major change in the cryptographic hash. So for example, if you look at these two, this is using the MD5 hash. The only difference between the patient has evidence of hypertrophy in these two cases is one case that it's a lowercase t, the other case is an uppercase t, a very subtle difference. Yet the cryptographic hash, as you can see, changes dramatically. And the other thing about a cryptographic hash, it's one way, or you try to be as one way as possible. In other words, if you give me a hash, can I create the message that generated that hash code? And with a good cryptographic hash, it is extremely difficult, if not almost impossible, to figure out what the message was that created that hash. So what would you use a hash function for? Well, it is used in encryption, but typically when you enter your password on a computer, it doesn't compare the password against a database. It uses a one-way hash to encrypt your password, and it checks the encrypted password against the database. That's so that if somebody manages to compromise the database, all they see are these one-way hashes, and remember, it's hard to go back, so they can't guess your password because all they see are these encrypted one-way hashes. It's used for data integrity, for digital signatures. Remember, any little change and the hash changes completely. So I can use the digital hash to determine whether or not data has changed. Remember in HIPAA, they talked about protecting the integrity of data. This is one way a technical means in which you can protect the integrity of data, is by using a one-way hash, a digital signature, if you will. In fact, a digital signature, typical digital signature is a one-way hash of the data you're trying to sign, which is then encrypted using public key cryptography. I encrypt it with my private key. I publish my public key to everybody. So when they get a signed document, they can use my public key to decrypt the one-way hash, and then recalculate the one-way hash on the document they just received and compare the two to see if they're the same. That way they know that I've signed the document. That's how a digital signature works. Hashes, though, are also used in indexing. Caleb was telling me of one of your applications where it's creating thousands and thousands of files. In order to break up the directories, it does a hash of the data to break up the directories into smaller chunks. We use hashes in TCIA, for example, to let's give you an example in TCIA. We'd like to be able to track patients longitudinally. So in other words, if we see the same patient, we want to be able to associate the existing records with the new records coming in for the patient. However, we don't want to know the patient's ID, because that would be a HIPAA violation, of course. So what do? We hash the patient ID. Okay? So the next time we see that same patient, when we hash the ID, it comes up with the same hash number, and that's what we store. So that way the record, we can tie the records together, but we don't know what the original patient ID is. It was destroyed in the one-way hash process. So now we're going to switch gears a little bit and talk about deployment architectures. So you've got these networks, you've adequately secured them, you've got these individual physical machines. Now, how do you deploy an application to these systems? And you actually, two of the big options you have is whether you're going to do a physical deployment or a virtual deployment. So what I mean by physical is I'm going to actually put the application on an actual physical machine. So this is great for applications that are really big resource hogs that do a lot of I/O, do a lot of reading and writing of the disk, or reading and writing from memory, or consume lots of CPU time. It's great to give them a machine where they don't impact other people if they consume all of the resources. It minimizes contention. They're not fighting against other applications for those resources. However, if you have an application that's fairly lightly used, putting that all on one machine is expensive, especially these days. Who remembers what Moore's Law is from last lecture? Some of you weren't here. Is he right? Okay, all right, so that's the distinction. Every 2 years, the number of transistors on an integrated circuit doubles. And typically that means the computing power went up. Well, nowadays the servers are so powerful that you'd have to have a really beefy big application in order to consume all the resources on a single server. So what people have tended to do is use virtualization. So this is where you have a single server, which then you load onto multiple independent virtual machines. And so this allows one piece of hardware to actually look like it's a lot of little pieces of hardware. So that obviously lowers costs, consumes less space and power. Because this virtual machine is a hypothetical machine, the hardware interfaces to that machine are consistent. You know, in a physical machine, when the machine gets old and I have to replace it, it's highly likely that the interfaces to the disks, to the memory, whatever, might have changed. Whereas with a virtual machine, you can keep them consistent. But the downside to virtual machines is that there's potential contention. If all the machines are trying to bang on memory all at once, they're going to impact each other. Yes, over here.
Chase switched on the virtual machine. Of course, quite humorous when they did it, because we had whole days where we got paid to sit at our desk all day because the whole system was down, because the volume was overwhelming the virtual systems they had, because they converted everyone over at once, basically. This, virtual network.
Yeah.
Pretty funny.
And they probably, and so virtual machines are not necessarily a panacea, but they can be extremely useful. All of TCIA, for example, from day one has been on virtual machines. So we only purchased 3 physical hardware servers for redundancy. So in case one went down, we had 2 more to take up the slack. But everything else was done in virtual machines. One of the advantages of the virtual machines is that, for example, if I have everything on a single physical server and that server breaks, my application is down. Virtual machines can be designed so that if the underlying, what they call hypervisor, the thing that the virtual servers run on, if it breaks, you can automatically migrate the application to a different server and restart it. So the virtual machines have a lot of advantages, but you have to, like the case of Chase, where they didn't probably plan correctly and test correctly for the loading, you could run into problems. Just between you and me, but if you quote me, I'll deny it. I think that was one of the biggest reasons why Epic had such a heck of a time rolling out here is because they did it all on virtual machines. And I don't think they had the capacity and loading correctly assessed. So it's similar to what happened at Chase, right? So what about cloud? A lot of people talk about, well, let's just deploy to the cloud. Well, what is the cloud? Well, cloud is just an extreme variant of a virtual machine. You're creating a virtual machine, but instead of running on your local hardware, it's running on somebody else's hardware somewhere else in the world. If you have very lightly loaded virtual machines, a cloud can be extremely cost effective. And it's also really great for things that are short-lived, where I only need it for a couple of months. Rather than go out and buy server capacity for a couple of months, you can contract with a cloud provider. However, one of the downsides with the cloud is security can be a concern. It's like anything. The more exposure you give something, the more threats that are out there, and the more risk you have for disclosure. So you have to weigh the security concerns against the convenience concerns. What's becoming more and more popular is something called a hybrid cloud, and that's where the core functions you keep on locally managed virtual environment, and less critical functions you let it spill out onto the public cloud. So you have this sort of, some people call this the elastic cloud, where as your loading goes up, you start pushing functions out onto Amazon or Google, and then when your loading starts to lighten up, you start shutting down those machines and bringing them back into your local environment. Cloud, there's different service models for cloud. Your client can either talk to an application that's running out in the cloud. All of you have probably talked to Gus, right? To register for classes. Don't ground too much. You hate it, yeah, okay. That the Gus is what is called, that's called software as a service. So the Gus server doesn't actually run here at UAMS, it's run by somebody else. You can have platform as a service. This is where you have databases or a web server or something like that running as a service, but we're still providing the content that goes into that database or application. And then infrastructure as a service, this is where I actually create my own virtual machine and I let somebody else run it. So as the diagram kind of indicates, you can actually do software as a service that's sitting on top of a platform as a service that's sitting on top of a infrastructure as a service. So there's a variety of, so if you hear this SaaS, PaaS, how do you say that? IaaS, YaaS? That's what they're referring to. Clusters. So this is going the opposite direction. Sometimes even a single server is not enough to get the job done. And so typically you'll do that with clusters. And there's we're going to talk briefly about 3 variants of clusters. There's what I call a distributed cluster, a high availability cluster, and a high performance cluster. So a distributed cluster are cooperating machines. They are not necessarily located at the same location. So it could be machines here in Chicago, in San Francisco, in Bengaluru, wherever, that are cooperating on a particular problem. Typically it's a functional division. Each one is doing a specific function and they all contribute back to the whole. And those functions, they typically are interconnected by a variety of technologies. The most popular and common these days is something called REST, representational state transfer, which is just a way of calling on a function somewhere else and getting an answer back. A more tightly coupled thing would be something called a grid, where the connections between the machines are more tightly defined. But that's typically what's meant by a distributed cluster. High availability cluster, which distribution does offer some high availability, but if one of those functions fails, your application may die. So high availability is talking about using multiple sets, potentially of distributed functions, but multiple sets of machines or clones that essentially mirror each other. And then you load balance between the clone. And there's two general broad groupings. One is called active-active. My clones, they're all capable of doing the job. So I load balance to all of my clones. That's the way TCIA operates. If you log in, if you go into TCIA, it will direct you to the most lightly loaded server. And that's the one that's going to service your request. It can also be active-passive, where I always go to one machine, but if that machine fails for some reason, there's something called a heartbeat that will detect that it's failed, and that will automatically switch over to the shadow machine, the passive machine that's been shadowing the main machine, and it takes over as active when the other one fails. And there are combinations of these things. So high performance, is trying to figure out what would be a good way to describe high performance. And yesterday I had IBM came in and we were talking about things. He had this great slide, so I stole it from him with his permission, of course. So what is the difference between virtualization, where I have lots and lots of machines, and high performance computing? So with virtualization, what you're trying to take is one resource, a physical computer, and make it look like a whole bunch of smaller computers. That's virtualization. High performance computing is in the opposite direction. I'm trying to take a lot of resources, some cases thousands of resources, and make them appear as if they're one computer. So each of these have their uses. Okay, if I have a lot of cooperating applications, virtualization might be the way to go to keep things isolated and separated. But if I need more compute power than what can be provided by a single machine, and I can't distribute it by splitting out functions and creating a pipeline between those functions, then that's where high performance computing comes in. So that's one of the big distinctions between high performance computing and virtualization. Yeah?
So how does something like Hadoop work? I mean, is it real high performance computing, or is it some soft approximation of that?
Hadoop is, I didn't move that. Hadoop it's a form of high performance computing, but instead of trying to, what it's trying to do is to maximize I/O throughput to the disks. So it's a way of dealing with data. And Hadoop is specifically designed to do a kind of problem called MapReduce. That's what it's targeted for. So it's a specialized high-performance, it is a high-performance computing architecture that is optimized for a particular class of problem. So, and you'll find that in high-performance computers. That's why I said makes lots of resources look like one, but I didn't say one of what, okay? Because different high-performance computing architectures are optimized for different classes of problems. So, for example, the one that we have here is optimized for what we call a massively parallel problem, where you have thousands of things all doing the same thing simultaneously. And they don't talk to each other. That's what's called massive parallelism. Hadoop, they tend to have to talk to each other because they're doing this MapReduce. So it's an architecture that allows you to do that MapReduce. Can I do MapReduce, for example, on our cluster? Yeah, sure. It may not be as efficient as on a cluster with dedicated Hadoop.
So for Hadoop, it definitely runs on a cluster. It's just different than some other architectures.
Yeah, the way the cluster is organized and interconnected differs in a Hadoop cluster versus a Beowulf cluster, for example. So, and we're probably going over the heads of most people at that point. So, but that's, you know, the key take-home message from all this that we've been talking about is just have some familiarity with the terms. With the terms, I would encourage you to go back and at least skim through chapter 5 in the book, if not read it. Again, it's sort of like I just did in the last 2 lectures, a 40,000-foot overview, but it might help refresh in your mind some of these ideas. Some of these things you may never have to deal with, but at least you have a familiarity with them, so if you ever did have to deal with it, you would know what you have to do to go dive in deeper to become expert in those areas. So from the book, we have about 12 minutes left. There are a number of discussion questions that I thought might be interesting to just open up a discussion here about the questions from the back of the book. So we didn't really talk about active versus archival storage. Does anyone want to hazard a guess as to what we mean by active versus archival storage?
Well, active, I would assume, is readily accessible in memory, whereas if it's archived, it's more compressed.
Less accessible is probably it.
Less accessible.
So active storage is stuff that I can get at right now within a fraction of a second. Whereas archival storage, it might take an hour or two, maybe even a day or two to finally get to the data. So if you're looking at companies like Google or Amazon who provide cloud-based storage, they'll sell it to you at different tiers depending on the speed of access. And there's no fine hard line for, you know, things that I might consider archival, other people might consider active. You know, but what are the considerations? Why would you keep some things in archival storage where you can't get at them very readily? It takes a day or two versus an active storage. Why would you pick one over the other?
For like the library world in our archives, certain things are used more often than others, so we'll have those in an area which they can be accessed quickly, but like something that maybe one person will look at every 5 years, we'll toss over in Glacier, which is an Amazon. It's a robot tape service that you mentioned. It takes anywhere from 2 hours to 2 days to get that.
Right.
And it's much more efficient. We're talking a penny a month per gigabyte as opposed to an AWS server, which would cost a lot more for that gigabyte of storage.
Right. So it has to do with cost versus access time. Now, how often is that data going to be used? And how quickly does it need to come back when it's being used? Because there may be some things that are only used infrequently, but if you don't have it right now, your whole operation stops. So where would you put that? I would probably put that in active storage, although maybe a lower cost tier of active storage, because there's significant impacts if I don't have it right away. Certainly things like databases that I'm banging on all the time, I probably would keep in active storage. What about backups of that database? Probably on archival storage. Okay. Explain how operating systems and cloud architectures insulate users from hardware changes. So we talked a little bit about that. And in cloud architectures here, I'm going to extend that to say virtual machines in general. But how does that insulate you from hardware changes? We mentioned it just briefly. So remember, in a virtualized environment, your program isn't running against the actual hardware, but rather it's running on an abstraction of the hardware. And that abstraction, because it's an abstraction, can be consistent even though the hardware generation underneath it might change. So that's why using operating, if you're writing to operating system interfaces as opposed to writing directly to the hardware, or using cloud architecture, that's how it can insulate you from the hardware, because you don't actually see the real hardware. it's emulated. Okay, what characteristics determine whether compute clusters or cloud architectures are better for scaling a given computational problem?
Your actual physical demands versus like what the hardware is versus virtual. I mean, it's all dependent on what your actual purpose is going to be.
Right.
Optimized for.
Yeah, what your purpose is, what it's optimized for. Another consideration is where's the data? Okay. So if all my data is local, does it do me much good to create a cloud solution? No. So part of it has to do with data locality. Part of it also has to do with resource utilization. If I have a really compute-heavy program and I stuff it out onto Google Compute, I'm probably going to rack up a really nasty bill. Okay. And there are some cases where a single node on Google Compute isn't enough. I'm going to have to create essentially a mini virtual high-performance computer. And people have done that. And you can do that, create a virtualized high-performance computing with a bunch of cooperating nodes that are working to solve a particular problem. But that's another thing, is the nature of the problem size. Can you compute it reasonably in one node, or do you need to divide it up into multiple nodes? How long are you willing to wait for the answer is another good question. Okay. Says explain how grid computing facilitates federation of resources. That question is going to be hard to answer unless you actually go read the chapter 5, because I didn't really go over grid computing. Anyone want to hazard a guess why I didn't go over grid computing? And I can hazard a guess as to why it's in the chapter. So one of the authors of the chapter is a guy named Ian Foster. He's considered the father of grid computing. I think that's why grid computing is in the chapter. Most of us think that grid computing is old and passé and nobody uses it anymore. So that's why I didn't put it in here. But somebody might ask, so grid computing is just a way of sharing resources across institutional boundaries. That was its primary purpose. So if I have, a high performance computer here and Jonesboro doesn't, how do they use it? It's just that over the years we've found easier ways to share those resources without having to resort to all the overhead of grid. Architectural advantages and disadvantages of different computing environments. I think we'll skip that one. REST and XML JSON. Again, the book only talks about XML, and folks who are in the know these days know that XML is actually going out of style. JSON is the what is XML JSON? Does anyone know what XML or JSON are?
JSON, at least I've been having to deal with it. It's like a database storage.
Not exactly. It's more of a representational encoding. Okay.
Based on JavaScript.
It's based on JavaScript. It's based on data structures in JavaScript. So JSON object, it's really easy to move a JSON object from storage on a disk someplace or in a message, the payload of a message is being sent into data structures that JavaScript can work on.
Pouring it into R.
Yeah. So, but the idea is by having a common data representation, it's like data standards. By having a data representation, it makes it easier to move data from place to place. REST, again, it allows you to break things up into cooperating functions instead of having one application that's monolithic all on one machine. You can break it up. You can actually divide out your services. For example, I have a medical record, I need to de-identify it. I could go out and get all the software libraries and de-identify it myself, or I can send it out to a de-identification service which will do the job for me and send it back to me, already de-identified. How can you prevent inappropriate access to electronic medical record information? Well, say again? Yeah?
You can house it securely.
House it securely?
Physical controls prevent reading in and badge access to level.
Right. So that identifies the user, and then what do you have to have on top of that?
Well, within the electronic medical record, even authorized users are not supposed to access certain records. So you need to have an audit trail if you want to detect the inappropriate access.
Right. So audit trail is a good way to detect that an inappropriate access happened, and then you can go holler at them, take appropriate action. The other thing that is you could once you know who the user is, there's authorization controls that you can put in play that says who can look at what data. Okay. And so we already talked about how do you detect it. Well, typically most people do it with audits. So every action that you do gets recorded someplace, and then you can have background processes that are looking at all of these recorded actions, these audit trails, to determine whether or not a breach has taken place. So you're asked whether a medical practice should outsource its information technology functions to third-party cloud providers. So what factors would enter into your recommendation to either outsource them or not outsource them? Think about that for a second.
Well, how secure is it? How secure is the information when you need it?
That's a good, those are both, you know, how secure is it? You want to make sure that it was secure, and you want to make sure that it's accessible. That you're,
Where is your information stored?
yeah, where is your information
Are
stored?
you a hospital network with multiple locations, or all interconnected, or are you possibly a single hospital?
Mm-hmm. Well, let's say I'm just a local doctor's office in I think at Walnut Ridge, Arkansas.
Cost.
What?
Cost.
Cost.
The amount to process the data, the amount to store the data, and the amount to retrieve the data. Because a lot of times, like with AWS, sometimes it can be super cheap to load everything onto the server, kind of run its thing, but when you go to pull off that data back when they're in, now all of a sudden you've got $1,000 bill and you're.
Right, but if I only have a small amount of data, that small bill might be cheaper than buying my own servers and going through the headache of trying to maintain them. A lot of people,
Pay the ransom.
you pay the ransom.
No, who's gonna pay the ransom? My sister's little baby hospital in Tennessee got their IT system hacked, and the hospital's the one that paid. Even though
Yeah.
I don't know what their rates are.
And a lot of people, you know, they think, oh, you know, why do I have to, you know, pay that company to, you know, all that money for this software when I just buy a little server? I come from a family of CPAs, and so maybe I'm slightly biased here, but, you know, why should I do, when I can buy QuickBooks and do my own books versus hiring one of my sisters to do my books for me? What's the advantage to it? Yeah, I can probably do it fairly cheaply myself. But when I get stuck, who do I go to? Right? So people tend to gloss over the actual cost of ownership. The total cost of ownership of something is not just the physical hardware and the software licenses that are needed to run the application. It's the care and feeding of that application with data. It's the backing up of that data and keeping it protected and making sure that it doesn't get lost if a truck runs into my front office and smashes my computer to smithereens. What happens to my data then? So unless you have staffing to try to keep that straight, sometimes it might be advantageous to pay maybe a little more money to have somebody else who knows what they're doing do it for you. So you're balancing these trade-offs. How much are you willing to get your hands dirty with the data versus paying somebody else to do it? I used to change my own oil in my car. I can still do it. I don't do it anymore. Why? Because it's, especially if you get a good coupon, it's cheaper just to have somebody else to do it. You know, So, actually, I should take that back. It's not cheaper, it's just more convenient for me to have somebody else do it. And the other thing is, though, that somebody else is doing it is going to look for other things that might be wrong in my car and warn me about them, mainly because they want to make more money, but let's not get into that. So there are advantages and disadvantages. There really is never one right answer. You have to weigh all the pros and cons and do that, like we said, that risk assessment to decide what is going to be the best way to deal with it. Well, that's it, unless you guys have other questions. Thank you.
All right, thank you very much.
You're welcome.
Thank you.
Well, hopefully it was useful.